Okay guys, so I was a little disappointed we didn't have more time in class to talk about geometry because I think there's some interesting bits that we missed out on. So I just want to take a couple minutes to show you a few things for Euclidean geometry. So one is, of course, the Pythagorean theorem. In vector form. Okay, so suppose you have two vectors, let's say x and y. These are somewhere inside Rn, let's say, and we want to assume that they're perpendicular, so x dot y is equal to 0. Then what do you have? Length of x plus y squared is equal to the length of x squared plus the length of y squared. It's one interesting little tidbit we can prove with not too much effort. So the proof is as follows. You simply take the dot product. Simply take the dot product of x plus y with itself. See, anytime you want to understand something about the length of a vector, it's useful to remember that the length of a vector is easy to understand if we square it. And the square of the length of the vector is x plus y dotted with x plus y, okay? And so, well, that's exactly x dot x plus x dot y plus y dot x plus y dot y. But hey, these were orthogonal, so we're given the dot product of x and y and x are respectively 0. And on the other hand, these remaining two terms, well, that's exactly the length of x squared and the length of y squared, and there you have it. Pythagorean theorem, n dimensions, about a minute. Now, if you have more vectors, right, it's not hard to prove. If you had, say, you wanted to generalize this theorem a little bit, right? Suppose you had, say, x1, no, that's not the right marker. Which marker do I want? Oh, so many choices. All right. So if you had, x1, x2, xn, pairwise orthogonal, which is just to say orthogonal. So I mean, xi dot xj is equal to, 0 for I not equal to j, then you could, I don't know, I guess you could just directly calculate it probably. Let's see here, so the length of x1 plus x2 plus plus xn squared would be what, x1 plus x2. Now probably I should do an induction here to be proper, but I will be improper. Just sketch the proof for you here. So when you take this dot product, right, the only thing that survives with x1 dot all of this, well, is just x1 dot x1, right? You notice that x1 dot x2 and x1 dot x3 and x1 dot xn, those are all 0, so I don't have to write them down. And then when I do x2 dot x1, it's 0, so the only thing that remains there is x2 dot x2. And you see how it goes down the line, just distributing, dropping the things which are 0, since we don't need to write them. We're just left with this. And there you go. There's the n-fold Pythagorean theorem, with not much more work, really. So orthogonality is important, understanding the relation between lengths of vectors. I think we can see that by now. So that's one thing I wanted to share with you. Another thing I want to share with you is proof of the lemma. So let me just jump over to that now. So the lemma that excuse me. The lemma that we claimed was what? What was that lemma? We said that if W was equal to the span of beta, then beta perp was equal to W perp. I might have used different letters, but that was the basic sentiment of the lemma. Is just that to calculate the perp, You don't need to use the whole infinite set if you don't want to. You can simply look at orthogonality with respect to a generating set. Okay, so that's what we're setting out to prove here. So, okay, let's see here. So what does this mean? So let's see here. Let's see here. We want to prove that's a subset of that. So let's let x be an element of beta perp, where we're assuming beta is a finite set. So let's suppose it's v1, v2, all the way out to, let's say, vk for the sake of being specific. Then to say that w is in beta perp means that x is in beta perp actually means that what? It means x dot v1 is equal to x dot v2, and so forth and so on down the line. X dot vk 0. All right. So I'd like to show that x is also in w perp, right? So if I have x, let's suppose that z is an element of w, right? So if z is an element of w, which is, by the way, the span of beta by assumption, then that implies that z is equal to a sum I equals 1 to k of ci vi, right? But we can calculate the dot product. Let's see here, x, x dot z, well, that's x dot that sum, and so by properties of dot product I can pull out the sum, but hey, x dot vi, I already know what that is, because we know that x dot everything in the basis beta is 0 because x is in the perp of beta, so this is 0 for each one, and so we get 0. Aha! We have just shown that as z was arbitrary, we've just gotten then that x is an element of the perp of w, because we just showed that it was perpendicular to an arbitrary point in w. So therefore, we found that beta perp was a subset of w perp. So then the converse direction, suppose, which might be really simple, I'm just not thinking terribly clearly at the moment. So the converse direction, suppose y is an element of w perp, right? Then what's that mean? That means that y dot w is equal to 0 for all w and w. Okay, so then it's immediate, but beta, of course, is a subset of w, and so we can just choose, so just, set y equals to, v1, and then set it equal to v2, and so forth, all the way down to vk. You can choose each one of these, and you get, obtain v1 dot, v1 dot y equal to, v1 dot w equal to 0, and so forth. Vk dot w equal to 0 for all w and w, and hence what? Well, oh, I don't need, I scratch that. I mean, that's true, but it's not really the point. Y is in the perp. I've just shown that y is dot product with 0 for each of these vk, but it's stupid. What does this show? This shows that, oh, I'm a stooge. Still an idiot. Alright, let's try this again. Let's see here, y dot w 0 for all y, for all w. Alright. So we have that this is true for all w and w, so I can set, I don't need to set y, I should not set y, that's the, right there. No, we don't get to set anything about y is arbitrary. But I can set w equal to v1, v2, vk. When I do that, this is not what I want. I mean, what I should say is, I just say, okay, so this is true for all w, right? In particular, it's true for w equal to v1 through vk. So then I get what I want. I get y dot v1 equal to 0, y dot v2 equal to 0, and so forth, y dot vk equal to 0. And that tells me that y is perpendicular to everything in beta, so therefore y is an element of beta perp. But y was an arbitrary point in w perp, therefore w perp is a subset of beta perp. And hence, thus we've shown what we set out to show, that w perp is in fact equal to beta perp. Which goes to show you that the thing we did in lecture wasn't wrong. It suffices to calculate the perp with respect to a generating set if you're looking at a subspace. And with that, I will stop punishing you with my voice.